So now we're ready to introduce this little notion called a modular function on a topological group. So roughly speaking, the modular function allows us to transfer between left Harmonic and right Harmonic, and it's going to be quite useful when we define the involution on the L1 space later on. So let's just get this ready. All right, so the idea is fairly simple. So let's start by looking at a left Harmonic. So let mu be a left Harmonic on some say locally compact Hausdorff space group G. And so it can do the following. So if I say for every y inside G, let's consider a new measure. Let's call it mu of y. If I want to evaluate at some set E, okay, so I can define it as basically mu of E right translate by this y, okay? So here E is every L. And as you can see, because the right translation is continuous, it's actually a homeomorphism. So we know this mu y itself is also a Borel measure and is clearly a Radon measure and so on. And one good thing is that this mu y is also left invariant. So if I consider mu y, if I want to left translate this E by X, then this is just E mu of X E y, okay? And by mu is left Harmonic, I can just cancel out the X on the left-hand side. This is simply mu of EY, which by definition is mu y of E. So this mu y is again a left Harmonic. So mu y is also a left Harmonic. And because we have this uniqueness theorem of left Harmonic, so mu y and mu, they're both left Harmonic, so you can find some constant. Okay, so let's give it a name. So there exists a delta of y, so this constant will depend on this y we translate on the right. So this delta y is going to be inside from 0 to positive infinity is going to be a positive scalar, so that I have mu y is essentially just equals to a scalar multiple of this mu. Okay, so that's from the uniqueness. And as you can see, this delta of y we just defined doesn't really depend on mu at all. Okay, so any left Harmonic is a multiple of mu, and you do the same trick, do the multiple of mu, right translate by y, you get the same delta y in the end. Okay, so this allows us to basically define that delta, if we treat y as a element inside G, it allows us to define this function from G to 0 to infinity. Okay, so this is y maps to delta y, we get a function. So let's give it a name, let's call it the modular function. So this is called the modular function. All right, so let's look at, first of all, let's do a little short proposition of what is modular function, the basic properties. So first of all, I want to show that this delta function, this modular function, if you treat the 0 to infinity as a group, multiplicative group, basically all the positive reals, and you do the multiplication as a group. So that's actually going to be a continuous group homomorphism. Okay, so it's G is a group. The right-hand side is also a group. It's going to be a group homomorphism, and it's going to be continuous. And second, I want to show that for every f inside your L1 of mu, okay. So if you want to integrate this f of say f of x, and of course, because your mu is left invariant, so if this integral of fx d mu is the same as the integral of fyx d mu, okay, you can put a y on the left hand side. But what if you want to put a y on the right hand side? Okay, so that's the idea, and it turns out you need is also kind of related to fx d mu, but you need to put this modular function of delta y. Okay, so in other words, if you want to translate on the left, then, well, by the left invariance, the integral doesn't change. But if you want to translate on the right, then you need to compensate by adding this delta function. Okay, you need to add this delta of y inverse. Okay, So that's kind of the idea behind the modular function. So let's do the proof. First of all, let's show it's a group homomorphism. So if I consider just delta xy of, if I consider any mu of E, then by definition of this delta, this is essentially I right translate E by xy. But you can think about it as translate twice. So you translate the EX by Y, so you get a delta Y of mu of EX, and you translate again, you get delta Y of delta X, and mu of E. So apparently you can cancel out mu of E, and as long as mu of E is non-empty, I mean non-zero, so you have delta of xy is equal to delta y delta x or delta x delta y. Doesn't matter because your range is abelian. Okay, so it's a group homomorphism. I'll keep the continuous later, so let's actually prove the second point first, and from there we can see it's going to be continuous. Okay, so to show the second point is fairly standard trick in measure theory. You consider a characteristic function first, and then you extend it by linearity to simple functions, and you approximate everything by simple function. Okay, so that's kind of the idea. So it suffices to consider to show for this f being a characteristic function on some Borel set E. Okay, so if extending from there to simple function and L1, you can just do it as an exercise. So let's consider what happens when your f is a characteristic function. So on the left-hand side, if you want to integrate f of xy, d mu x, okay, so this is essentially just integrating this chi of xy, d mu x. And if you think about what happens when, so here y is fixed, what happens to the chi of xy? So chi of xy only equals to 1 if the xy is inside E. Okay, so xy is inside E. Well, that's even only if the x is inside the E translate on the right by the y inverse. Okay, so this is essentially just equals to the measure of E y inverse. Okay, and because it's translated on the right, I can move the y inverse by the modular function. So I get a delta y inverse and I get a mu of E. And this is just y inverse integral of chi d mu, which if you write it back using f, this is integral of fx d mu of x. Okay, so now you have it for characteristic function, and you just extend it. All right. All right, and now we have this formula, so we have a pretty good idea of what this delta y is. As you can see, if you fix some f, which is, say, in a compactly supported function and is non-negative, then this on this side, the integral of f d mu is going to be non-zero. It doesn't depend on y, so it's really just a function of you integrate this one particular function where you translate by the y on the right. And we know the translation map is a continuous map, it's uniform continuous. Okay, so if you recall the Ry of f, evaluated x is just equals to f of xy. And because we know that this map, f maps to Ry of f, is a continuous map as y goes to the identity you have. This is f, Ry of f is converging to f in the uniform norm. So based on that, you know that this integral is going to be continuous in y. All right, so and your delta y inverse is, well, y inverse is clearly continuous, so delta is continuous. Okay, so you can convince yourself this delta is continuous from that. All right, so let's finish the proof, and let's do a immediate corollary. So the idea is that if you recall, so if you recall the following when we first talk about the Haar measure, is that if I give you a left Haar measure, so it is a left Haar measure, then I can define a new measure. Let's call it, maybe give it a different name. Let's call it rho of E. If I define to be mu of E inverse, then this is a right Haar measure. Okay, so we proved this in the last week. So this is a way to transfer between left and right Haar measure. And it turns out this rho of E can be defined using this modular function. Okay, so let's do the corollary. So in fact, I have this row of E. Okay, so this row, what you can do is you can write as delta x inverse of, or you say D row is equals to d mu of x. Okay, what do I mean by that is essentially just saying if you want to integrate anything, say fx d row of x, well, that's going to be the same as you integrate the fx, you replace d row by the other one, so delta x inverse d mu of x, okay? So that's basically what we want to prove. And so how to prove that? Well, first of all, let's consider the integral on the right-hand side. So let's just define, say I of f, okay? So say I of f is equals to the integral of fx delta x inverse d mu of x. And let's consider what happens if I want to translate things on the right, okay? Essentially, I want to show is basically the linear function given by the rho. While rho is a right Harmonic, so let's first show that this I is actually a right invariant integral, okay? So let's think about what happens if I want to translate on the right. So if I consider fx delta x inverse d mu of x, if I want to translate things on the right, then I need to compensate by adding this delta back. Okay, so let me just bring you the formula we had before. So here is the formula. So essentially it's saying if I want to add a y on the right, then, well, this is on the right hand side, this is my original integral. If I want to add a y here, then I need to compensate by delta y inverse. Another way of writing that is essentially just moving the delta y inverse to the other side. So this is equivalent to if I say integral of fx d mu of x, okay? That's going to be equals to the integral of fxy d mu of x, and then I do the delta y here, okay? So here delta y inverse, the 1 over delta y inverse is just the delta y, okay? Because delta is a group homomorphism and map the identity to identity, okay? All right, so this allows us to say, well, now I have an integral. I want to right translate everything by y. So I have fxy, everything translate by y. I have xy inverse here. And then I have a d mu x. And the compensation is I need to multiply delta y here, okay? And again, here, the delta is a group homomorphism. So the x inverse y inverse is basically delta of x inverse y inverse. So this becomes delta of y inverse. Delta x inverse is just scalar. We don't care about the sequence. And you move the delta y inverse outside, and they cancel out the delta y outside. So this gives you the integral of fxy delta of y, sorry, not y inverse, but x inverse again, and then dx, d mu x, okay? And if you realize, well, this is, if you think about as an integral of your fx, okay, or fxy, then basically this integral is right invariant, okay? So in other words, your measure you defined by multiply this d mu by delta x inverse is a right invariant Haar measure. So now we prove that this integral we just defined is right invariant respect to this f. So we integrate fx, and that should give you the same integral when you integrate fxy. So we know that if we consider this, maybe call this this new measure we define, mu prime, rho prime is basically delta x inverse times mu, or let's do the d mu. Okay, so we have that rho prime is going to be a right Haar measure. Okay, so that's going to be a right Haar measure. So now we have rho is a right Haar measure and rho prime is a right Haar measure. So by the uniqueness, they have to differ by a scalar. Okay, so by the uniqueness, there exists some constant c greater than 0, so that this rho prime is essentially just c times rho. Okay. All right, so essentially now we just need to prove that this constant c is equals to 1. Okay, then we should be done. So how to show this c is equal to 1? Well, let's consider the following. So for every epsilon greater than 0, because your delta function is a group homomorphism, it maps the identity to 1. Okay, so there and the delta is continuous, okay, so there exists some neighborhood of the identity. Let's say V is open, neighborhood of the identity, and we can just make it symmetric, so that my delta function is close to 1 on this neighborhood, okay, so delta restricts to V minus 1, okay, that's going to be less than epsilon, okay. So now because of that, if I want to compare C row of V, and we minus the mu of V, okay. If I want to compare these two, well, on one side, because this V is symmetric, I pick it so that V and V inverse are the same. So rho of V and the mu of V should be the same, okay. So this is on one side. If I do the absolute value here, so on one side, this is just equals to C times mu of V minus mu of V, okay, which just equals to C minus 1 times the mu of V, okay. And on the other side, okay, so C times rho is just the rho prime, so let's just replace it by rho prime, and then we minus mu of V, okay. And well, rho prime is given by this integral, so let's just write it as the integral, okay. So this is going to be the integral over V of, let's write them together. So for the rho prime, I have the delta x inverse d mu of x, okay. And I minus another copy of mu, so mu of V is just equals to the integral 1, so you minus 1 here. So this is less than equals to the integral of the difference between the delta of x inverse minus 1, d mu of x. And you realize, well, when x is inside V, we have, by our choice of V, is this delta minus 1 is close to 1, close to epsilon. So this whole thing is less than epsilon times mu of V. All right, so because V is open, we saw mu of V is going to be strictly positive. So we have C minus 1 is less than equal to epsilon for every epsilon. So this proves that C is actually equals to 1, okay? So let's finish the proof. And I just want to point out one thing. So one consequence of this is that, well, there are actually two things I want to point out. First of all, you may tempted to say, well, this formula here, really what it looks like is just d rho over d mu is equal to delta x inverse. Okay, it's a changeable variable formula, and you may tempt to say, well, this looks like rather Nicodim derivative. Okay, in fact, you can clearly see the rho is absolutely continuous with respect to mu. Okay, so if one is 0, then the other has to be equal to 0. Okay, but you can't really use the Radon-Nicodim directly. Okay, so because your group may not be sigma finite. Okay, but after you develop the modular function from the right translation, you eventually reach that this derivative looks like a derivative of these two measures. Okay, so it's technically not a Radon-Nicodim derivative. And another thing I want to point out that this new modular function allows us to do the integral in many different ways. So for example, maybe I should just write it as a corollary. So if you want to say do the integral of fx dx, and you want to relate it to something about the integral of x inverse, let's say the mu of x here. So mu is your left-hand measure. So if you want to somehow transfer your function from fx to f inverse of x, then what you need to do is you need to compensate by x inverse. Okay, so this is an easy consequence of the proposition we just proved.